Yeah. Are we good to start? Yes, good. Yeah. Are we good to start?
Is it work? It does work, it seems. Yes. Woo. Hello. So many of you are here. This is really, really amazing. I think we never had so many people in the room as today. So I'm really happy. Thanks for you being here. Tiny applause, please. So welcome to the fifth time that we do the Munich Science Slam, and we really can't believe that it's already the fifth time, because when Nick and me, we met like last summer and had this idea, we didn't really dream of like having so many of you here, and that this actually is something that people are interested in. So we're really happy that you are here, as I said. And when I say we is me, I'm Alex. Nick here at the on the very left. Then we also have our team. Team, say hi, please. Hi. Wave. Hi. And all the helpers. And without them, of course, nothing would have been possible. And so you will see them around a lot. And very first question. Of course, I have to do this for legal reasons. We have a photographer. What photographer? Wait. And everybody who does not want to be on a photo, please raise hands now. So please, don't photograph her. And here at the very back also, are you sure? Please? Yeah? Okay. Okay, then we have done that. Everybody else, smile. You might be on pictures. Okay, great. Well, yeah, cool. So we can finally start. So why are we all here? So we have a mission. Our mission is to boost communication among scientists. And how do we want to do this? We want to do this by improving presentation skills, because we all know that scientists actually can be pretty bad at presenting stuff, right? So we want to improve that. And also, we have the mission to actually understand and find out what actually a good talk or a good presentation is. And we have been doing this in the last 4 slams, and we also still try to do this today. So, and what makes us special, we think, in comparison to all the other science slams that are out there, is that actually we are a by scientists for scientists event. And so we hope we have a lot of people here in the audience that have a diverse background, and the talks are, I think, very understandable also for people who have a non-scientific background. But yeah, we actually trained our speakers beforehand in a presentation skills workshop so that they actually know what they're doing. And what you might have heard already, because you entered the door and our friendly helpers, they asked you to put your name in a box, because our event lives from an active audience participation, right? So you will later hear what's that really about. But this is really one of the cores of our event. And also, we think we're just at the niche between one of those top science slam talks and this hardcore science talk. So don't worry, there will be really good talks here and not dry science today. Not all. You will learn something. Be prepared. And yeah, just to give you a short glimpse on what has happened since last summer, when we had our very, very first event. And we had this at Burda boot camp, which was a room that was a quarter the size, and we still had 70 people cramped in there. So we definitely learned that this room was too small. Back then we had 10-minute talks and 1-minute talks. And we had the very first version of our feedback system. What we have learned, as I said, room way too small. 1-minute talks felt very short, even though they were very interesting and entertaining, they were quite short. And also, we learned that our concept works and that live coding skills by my colleague Nick here are very on level 100%, and this also will happen today again. And also, a tiny note, so here in the back, this is Amanda. This is one of our very first speakers. She's here doing this video. She joined immediately as a helper in the team because she liked it so much. So that was a good proof for us that actually our system works. And we continued. We then went to Google for our workshop, and we had a JetBrains, our very first event here. We had, again, still 10-minute talks. We increased the 1-minute talk length to 2 minutes, and we already had 120 people in the audience for the second time. And we changed the voting system a little, and what we learned is that 10 minutes are still too short, 10 minutes are too long, 2 minutes are too short, and we also learned that our voting system is a bit complicated, and we also learned that the after party is a good idea. But back then the problem was we switched to the 5-minute version talk that we also have today, because we felt this is actually something that's a good length. We introduced the improv talks that you will also hear about in a second. We again had a full room with 120 people. We had voting system number 3. And we definitely learned that 5-minute talks still actually, this is like something where you can put information in, and it's still not so long that people might get bored in the audience. And voting system was still pretty complicated. And of course, there is never enough pizza, which is probably the same today. And yeah, we changed the whole thing again for the last Science Slam that happened only this year in June. And we had a lot of speakers there. So we had 13 5-minute talks. We had those improv talks that were still really nice and working really well. We had more than 120 people in the audience. And now finally, we have a voting system that's based on the Google Forms, and we will also do the same thing today. So we learned that this actually works. And we also learned that most of the talks were neurobiology based, so there seems to be a lot of neurobiology in Munich, or just because of the reason that Nick and me have a neurobiology background, and our friends, we just force them to be speakers. I don't know. And yeah, so what we definitely learned is that we need to have an after party to keep on discussing, because last time we just entered a bar, they were completely overwhelmed, but it was really nice, and we kept discussing until 2 a.m. in the morning. So that is why we do have an after party today, an official one, and the bar knows that we are coming. So what happens today? Still change the whole thing again, and we still want to find out what a good talk makes a good talk. And yeah, so we have the team, as I already mentioned, and without them, really nothing would have been possible. You wouldn't have seen any of the ads on Facebook or Instagram. You wouldn't be able to eat and drink with you today, or the speakers wouldn't be able to maybe get some prizes in the end. I'm not saying too much here. But yeah, so thanks for the team and all your help, really. Big thank you, of course, goes to our sponsors, because without them, really nothing would be possible. So thanks, of course, at the very first place to JetBrains, that they allow us to be here, that they feed us, and that they give us beer, and also Mama. But yeah, thank you for having us again. We really always enjoy being here at JetBrains. Then Google hosted us for the workshop. Thanks for that. And then Synergy sponsored a big part of money, so we can actually finance prices, T-shirts, and everything. And thanks to my graduate school, the Impress for Life Sciences. They hosted us for the rehearsal, sponsored also pizza. Yeah, we live on pizza actually. And the Life Science Society also sponsored some prizes, as well as the Freie Staatsministerium für Bildung und Kultus und Wissenschaft und Kunst. Thanks for them. They also sponsored us with a lot of prizes. So thanks to our sponsors, and please applause. Thank you. So what's going to happen today? So today we have 2 rounds of 5-minute talks. And each talk consists of the talk itself, then we have a rating, and in parallel to that, we have an improv talk. They'll tell you what exactly that will be. Then, of course, we have a break in between where you should mingle and talk, have a beer, just get to know each other. I hope many of you also have the sticker where you have to put down your affiliation or your job or whatever you're doing, so you actually can ask the other person, hey, this looks like a computer, what are you doing? So please, this event is for communication. So also use the break and the after party for the communication, okay? And then, of course, we have the second round of talks. We might have some prizes, and then we have the after party at the Stragler Bar, which is 20 minutes away by public transport or walking from here. So I hope to see many of you there. But yeah, so if you haven't logged into the Wi-Fi, you have a chance to do that now, because you do need your phone. because it's an active participation, right? So please log into the Wi-Fi or just have a very good internet connection. Because our feedback system for today consists of 3 parts. Yes?
Just one small remark, in the password it should be lowercase, right?
Oh, yeah.
Yeah.
That's the point.
Exactly, that's what I
I
thought.
am very sorry, yeah. So this is all lowercase. Sorry, I hope you can log in there. Good point. Okay, so today's feedback system consists of 3 parts in total, okay? The very first one happens after each single talk. What happens there is that you can go to our website already, that is munich-science-slam.com, and you will find on the very top 2 buttons, 2 red buttons. The first button says speaker rating. So you just go on there and it leads you to a Google form. You go to the Google form, and after each talk, you select the name of the speaker. You first rate how much you like the talk, with 0 being, yeah, not really, and 9 being, oh my God, this was the best talk I've ever seen in my life, okay? And then you also, very importantly, you actually choose words that, in your opinion, describe the talk the best. There is a list of words that you find, and you can choose any words that you think describes the talk best. There are positive words, there are also some negative words, and just really give feedback, because we will have some very interesting data to analyze from that. And this is roughly how it looks like, a Google form. I hope you've seen that already, but I think it's very self-explanatory. And then, after the whole thing, so after all the talks were given, we have another rating. And this is the rating where you do vote for your favorite talk. So you again go to the website, you click the other button that says favorite talks, and then what you do is you choose your 3 favorite talks. So the most favorite, the second favorite, and the third favorite talk. And you also please indicate why you choose those talks are the best ones. So what factor made you decide that? And also give feedback about what could have still be improved about these talks that were actually good. Okay, so, and then, so this is how it looks like. I hope you all seen a Google form already. Yeah, and then now you want to know what's with the improv talks, and everybody who has the name in the box might be very interested now. Okay, so what we're going to try today is also new again, but what we want is that before each talk, what we want is that one person during the talk draws a tiny sketch about what the person was saying. So just the main point that you remember, just make a tiny slide basically. And in the very back, we do this in the very back, so of course nobody can also see what you're doing and you don't feel pressure, so it's very there. And you draw it, and then after the talk, you come on the front, and person number 2 uses your slide summarizing the talk in his or her own words using the slide, okay? So I think this will be a lot of fun. And don't worry, even if you don't, like, if you're a biologist and there's a physics talk, I've heard the talk, I'm a biologist, I do understand what it is. So then, don't worry, and it's a lot of fun. Okay, and you know before the talk who's the improv speaker, so you don't have to sit in fear or whatever, right? It's a lot of fun every time. Okay, cool. So, do you have any questions? Is the Wi-Fi working? Anything unclear? Then that's the chance. Otherwise, we start right away. Yes.
I just want to make a comment.
Yes, please.
Hi. So I'm seeing the data come in live. I'm writing my Python code live to analyze the data. We'll present at the end. It's a lot of fun. And I have to say you guys are amazing or completely unamazing already. I can tell this. Because no one has put any input yet. This is the first Science Slam where before the first speaker hasn't come up, someone hasn't voted to decide that someone is. So thank you so much.
Okay, cool. So that's really amazing. That's new. So okay, and also feel free to go on our social media and use the hashtag #MOOCScienceSlam5 if you feel like tweeting, Instagramming. But yeah, so rather pay attention to what's happening here. But you know, if you want to. You can always go on the social media. All right, cool. So then I would say we can start with our very first talk. So this is the schedule for the very first round. We have 5 talks in the very first round, and the first speaker in this round is Ida. I don't try to pronounce your last name. I just stick with Ida. And the title of her talk is Dear Brain, What's Going On? You can already come on stage. Yeah. And we can have a small applause. Her background is in biotechnology, and right now she's a PhD candidate at the German Center for Neurodegenerative Diseases. And interestingly, she grew up less than 200 kilometers away from the Arctic Circle. So right now it must be very warm for you here. Yeah. Okay. And as a kid, she was a very dedicated rock collector. So if anybody shares this passion, please talk to her. And actually, she also has won the Swedish Junior Championship in ice hockey. So not only a smart girl, also a sporty girl. So very good. Okay, so we just do the unconnecting of the computer. Wait a second. Okay. Right. Okay. And then what? Okay. So yeah, Ida, the stage. Oh wait, stop. Oh yeah, stop. The improv talk, I always forget them. Okay, so my colleague Marita is drawing the name and telling us who is the first person who will be drawing a slide. Everybody's scared. Okay.
So the draw for this slide will be David Silva.
Where is David? So you can come up and go to the sketch. I'll show you what it is.
And the second improv talk who can then present his drawing is Kay Shellberg.
Kay. Nobody wants to? It's you? Hi. All right, cool. You can't sit down. You can stay seated. You have to stay seated. Don't look what he's drawing. That's the whole thing. All right. Okay, so Ida, then, I didn't forget anything. The stage timer?
Yeah.
Good. The stage is yours. Thank you. I think everyone can hear me, right? Okay, good. So good evening, everyone. My name is Ida Pesma. I work at the German Center for Neurodegenerative Diseases, and we also have a lot of projects within the Munich cluster for systems neurology, Synergy, which is the sponsor also for this wonderful event. Tonight, I'm going to steal 5 minutes of your time to talk about the brain, and the title of my talk is Dear Brain, What's Going On? So I want to start off that you imagine yourself being in a place where you're surrounded by people, for example, in the line in the grocery store, or here in the audience, and the person next to you sneezes. Usually we do not find this very pleasant, and that's because we know that this is a way for bacteria and viruses to spread, and they can make us ill. However, luckily for us, our body has an immune system to fight this. But during this fight, thanks for the wonderful example. But while this fight is going on, we might develop fever, for example, and fever is a perfect example of an inflammatory response. So that's the body making a response against a pathogen in order to fight it. Tonight, I will tell you about inflammatory response in the brain. But before I get started, I want to tell you why this might be interesting for you to listen to. Because this is you, and whether you want to face it or not, you are not getting any younger. And that's true for all of us. We're getting older and older. And inflammation in the brain seems to increase with age, together with diseases such as Alzheimer's disease and Parkinson's disease. But what is actually happening then? Let's take a look at the brain. Here is the neuron, the most famous and popular cell type in the brain, and it always steals the spotlight.
But it is for a good reason, because this neuron connects to other neurons and make up a signaling network, making it possible for us to do whatever we want to do. But there are also other cells in the brain that support this neuron and make sure that the signaling works. One cell type was long forgotten about and thought to be just a bystander, mainly because it makes up such a small part of the total cell population in the brain. And tonight I want to shift the spotlight to these cells. They are the immune cells of the brain, also known as microglia. Now, these immune cells, or microglia, might not look like a lot to the world, but the cool thing is that they can get activated. And then, well, they still might not look like a lot to the world. And you might wonder, what kind of scribbles and doodles have I been making here? But it's not so far away from the reality. Here are actual images of these. So to the left, you can see before activation how these cells have their processes to be able to search the environment to find something bad. And once it finds it, it gets activated and it can eat it. That's what you see here, that these red parts in this cell, it has already been finding something and starts to take it in. Interestingly, the activation of these cells has been described to be good, but it has also been described to be bad. And I think we should be careful with calling something bad before we fully understand it. So tonight, to describe these cells, I want to describe them as Pac-Man. So whenever you see this symbol in my talk, it represents an immune cell of the brain, also known as the microglia. And I choose the Pac-Man simply because these cells like eating. So why would some people then call this bad, these cells? So here we have the famous neural network with a signal going through. And for some reason, the immune system has been activated in the brain. For example, because of waste accumulation, which may happen over time. And when the immune system is activated in the brain, and there are even studies suggesting that these activated cells can start nibbling on the connections between neurons. And when a connection is lost, there's always the signal. And whenever we lose a connection or function in the brain due to neuronal loss, we call it neurodegeneration. And this is causing, for example, dementia. This is also why people would want to treat this kind of information and why we consider it to be bad. And now you might think, dear brain, what's going on? Why is this woman telling me that I have bad Pac-Mans in my brain? Well, remember, there was also a good side to it. And we should really consider this. Would the body invent such a function and such a cell if it wasn't any good for us? So here again, we have the famous neural network, and it's working fine. But then something happens without an immune cell being involved. This cell can get injured, or it can even die because of various reasons. And then, luckily for us, we have the immune cells, and once they are activated, the activated microglia can take away part or the whole of this cell. So this can be repaired or fully replaced, and the signal can be restored. So tonight, I have told you about the immune cells of the brain, also known as microglia, and how these cells are being activated. And once they're activated, they can sometimes be bad, but we also know that they are good, and that we will really need this type of activation. So scientists are trying to find out what type of activation and what type of situation would be beneficial or detrimental. And this is also why some people would then want to treat the bad information, maybe even drive back the activation. But I want to emphasize that we should not forget about balance in this case, so that we do not lose the beneficial effects of these cells. And therefore, for example, for my PhD project, I searched for markers for different activation states, and I would be happy to discuss this during the break. And with that, I'd like to thank you for your 5 minutes, and dear brain, thanks for being more than just neurons.
Okay, so now we have to quickly switch again. No, we switched
So we
again.
can use as many words as you want.
Yeah, so you remember what's happening now. You log in, you go to our website, you get the Google form that says speaker rating, and then you choose EDA, and then you say how much you like to talk, everything between 0 and 9, and then choose, as Nick pointed out, as many words as you feel should be described, should be used to describe EDA's talk. Yeah, thank you. The speakers have to work themselves here. Okay. Yeah, so as many as you want.
Yeah, but why was structure not in negative words?
Oh,
Is it?
that was,
It is.
It's a
Mm-hmm. Is it?
for good reason.
Yeah, okay. You do have reason for that. You will know later. Okay, while you're doing this, I hope that there is a nice drawing at the very end. So can you just rip it and come in the front? A few moments. Yeah, okay. Okay. Right.
What was?
Go ahead. No? Okay.
Why do we have to put
You don't have to. Just
Yes.
are you
Question.
It's a required question.
Then think of some. Yeah.
What?
Okay, we can change that. It's everything is live here, so if there's nothing bad to say. Okay. Yeah, just a minute for live coding. Yeah. Okay. You don't have to draw eyes. All right. As soon as you're done, doesn't have to be super pretty. Don't worry. Hurry up. So to increase the pressure, Kai, are you ready with voting? Are you still voting? You can refresh the page if you want, and then the negative is not only not the whole thing, just the paper. Cool. And please come also in front, David, with the paper. And Kai. All right. Yay. Don't hurt yourself. All right. Hi. Yeah, I have to join. All right. Yeah. You're allowed to help only, but you can use the drawing to explain what you see. Yeah. So maybe you can help it. You can hold it.
Yeah.
You hold it, right? All right. Okay. So I think you have to come a bit more here because it's in the projector. Maybe. I mean, we tried this the very first time, so let's see what's happening. Higher. Like this. Not everybody sees, I think. Maybe you can like walk. Like okay, we're gonna try that now. Okay, so hi. I use the microphone, so summarize talk in your own words. Have fun. Have fun.
Some people remember Pac-Man. You see the Pac-Man? Maybe it was a game. Two about okay. Meeting was before Pac-Man find out. I don't know what he find, but he find some microbes also, and
You can also just say what you remember.
yes, zero to 100. Okay, as you get. Yeah, okay, and after them, maybe 100 times in the game.
David, you're allowed to help. Don't worry. Yeah.
It's okay. Yeah, that's the other version. The other version that you're behind our head. Okay, but the other one is better to see.
You can just summarize also what you personally remember. Or David also helps you doing this.
Did it use
Mm-hmm.
well? The number is better.
You can speak louder. Don't worry.
You can.
Wait, I help you.
Thank you. There's a part in between that I'm not too sure about because I was trying to try. But then, in normal conditions, you get exposed to several bacteria throughout the day. Someone sneezing onto you. That's not pleasant. As you get older, your immune system grows weaker, and you have a response from the immune system in the form of this Pac-Man, which is activated, and then you can choose to change this cell, which I don't remember. I cut it, a neuron. Oh, sorry. Can then try to fix the neuron.
Yeah.
All along.
Okay, great. Thanks a lot, guys. So, yeah, that's a lot of fun. All right, I'll leave that here. Ida, if you're interested, you can take that later. Okay, cool. So I hope you all finished voting for Ida, and then we can go on to the next talk, which will be from Konstantin. Konstantin's talk is titled Twinkle, Twinkle, Little Laser. And he has a, where is he, by the way? You can come. Don't be shy, stage, you know. He has a PhD in atomic and molecular physics from Imperial College London. And right now he's an R&D laser physicist at the Top TPAL Project, GmbH. It sounds weird in English, I'm sorry. What is nice to know about him is that he went traveling for 20 months between his PhD and his job. And he went from Alaska to Ushuaia. All right, okay, thank you. And not only an old fire truck, but also on his bike. So if you want to talk about traveling, he's the right person to talk to, I feel. So, okay, then we do another round of improv names. I hand over to Marita.
So the first improv talker who is drawing there in the back is Matze H. Where is he? And the second person for this talk is Hai Long.
Right? Always, yeah, it's there. Okay, so the improv painters and listeners and speakers are ready? Yeah? Okay, cool. Everything technical is working. So yeah, have fun. The stage is yours, Konstantin.
Good evening. I'm Konstantin, and I work for a small company that produces lasers that you shoot into the night sky to create artificial stars. Now you may be wondering, okay, but why would I want to do that? And so imagine you're an astronomer, and all the objects of your heart's desire are out there in space, but you're stuck here on Earth inside the atmosphere. And the atmosphere is great because it means we can just breathe without having to wear spacesuits at all times. But it also means that you cannot get sharp images of your favorite galaxies. And so you look up there, and everything you see is just a bit blurry, and maybe something hurtling towards you, you just can't really tell. Why is everything so blurry up there? Well, let's say we're looking at the birth of a new binary star, and the light from this cosmic crystal thing, it travels through the vacuum of space for years and years and years, minding its own business. Nothing ever happens to it, until in its last 100 kilometers or so before it reaches your telescope, it encounters the atmosphere. And the atmosphere, well, it just jumbles up all that light, and by the time it gets to your telescope, it's a right mess. And so what do? Well, first thing is you build your telescope on top of a mountain, you get a little bit closer to the stars, a little bit less atmosphere to contend with, and it does improve things, but it's really not quite enough. But luckily, astronomers are quite a clever bunch, and so they came up with this technique called adaptive optics, that somehow allows you to compensate for the effect that the atmosphere has on the light on its way through. So how does that work? Well, the light coming from whatever you're looking at, it gets jumbled up by the atmosphere, and then it gets reflected when it reaches your telescope by this thing called the deformable mirror, and we'll come back to that in just a second. It then travels to the beam splitter, and the beam splitter, it does what it says on the tin, it splits the beam, and part of it travels to a thing called a wavefront sensor. Now that's just a special type of detector that can measure what the atmosphere does to the light on its way through the atmosphere. And that information is then fed into a computer that calculates in what way the deformable mirror has to change its shape in order to compensate for the effect of the atmosphere. And so the light that is transmitted by our beam splitter is corrected before it reaches your camera, and you can get sharp images. This technique works extremely well. So before you upgraded your telescope, this is what a photo of Neptune would have looked like, basically just a blue blob. And now with adaptive optics switched on, you can make out features on the surface. And essentially, if we can get sharper images, we can learn more about what we're looking at. There's just one little problem with this technology, and that's the special detector I was telling you about, the one that measures what happens to the light on its way through the atmosphere. Very light hungry, meaning we can only really use this technology when we're looking at something that's really, really bright. And it turns out that even most stars just aren't bright enough to defeat our detector. And so, remember in the beginning when I told you that I worked for a company that produces lasers that you shoot into the sky to create artificial stars? Well, this is where we come in. And you get one of those lasers, or 4 in this case, and you bolt them to your telescope, shoot them into the night sky, and now you can create an artificial star that's bright enough for your detector to work whenever you need it, wherever you want it. And how does that actually work? Well, it turns out that in 100 kilometers altitude, and when they're excited, they emit light, and that's our guide star that we can use for our detector to run. And the results, they're pretty similar. So if you use a laser guide star or a natural guide star, the result is pretty much the same. You get sharper images, whether you're looking at Saturn or satellites, that's up to you. And so why is this important? Well, I think firstly, it allows us to learn more about our universe and to satisfy our natural curiosity. And for that, we need sharper images. Secondly, there's more and more satellites circling our Earth. But at the same time, unfortunately, there's more and more space rubbish flying around out there. And this isn't more satellites. This is just the additional space rubbish produced by a single collision of 2 satellites in the year 2009. And a lot of these satellites, they're responsible for flight safety, for GPS navigation, for weather forecasting. So we really do want to keep them safe. And in order to do that, we need to be able to properly map and get sharp images of what's going on up there. And thirdly, there's a whole bunch of asteroids and comets and stuff flying around out there. And with adaptive optics, well, hopefully we can get more news like this. But on a more serious note, if we can determine the trajectory of these bad boys with high accuracy, then we will be able to predict future collisions between them and us, and hopefully we'll be able to do something about that. And for that, we need sharper images. So thank you very much for your attention.
All right. So you know what to do. Get your phone, choose Konstantin, and do your voting. Say how much you like the talk, between 0, not really, or 9, a lot, and choose the words to describe his talk. And this gives our improv artist a bit more time to finish his drawing, and our improv speaker a bit time to think also. All right. So, do your voting, think about how to rate his talk, think about what words fit to describe his talk. Choose wisely. Okay. Is the improv speaker ready? Can come on stage already? And as soon as our improv artist is finished, he can come on stage. Okay. What was your name again?
Hilo.
Hilo. Okay. So to make it a bit easier, so using his slide, just tell us in general what the talk was about.
Okay.
Tell us one new thing you learned.
Okay.
Maybe it was a lot, but just like one new thing that's stuck in your head.
Okay.
And tell us what you really loved about Konstantin's talk.
Sure.
And also, hopefully, using a very nice slide that you can use to describe.
Okay.
Yeah? Okay, so what was it about? What you learned and what you really loved.
Okay.
Yeah? Okay. So there is an artist coming. Maybe you can come here a bit.
Okay.
All right? Hi.
Hi.
What was your name again?
Matze.
Matze. Hi, Matze.
Hi.
You have a very beautiful. Oh, that's really cool. Is it high enough? Does everybody hopefully?
I'm not there.
I know. Okay, well, we're gonna try. Okay, so summarize your own words.
Okay, so I think the talk to me is pretty clear. So develop a technology to help us or help the telescope to see more clear of the space, for example, the stars. And I think the key words I remember is adaptive optics. And then they shine the laser light, and then to understand the path of the light, and then correct the path, so then allow the telescope to see more clear. So let's say also imagine then the sky is like a universe. You want to see more clear through the sky or the atmosphere. That's what I understand. Yeah. The beam splitter is going to be a very important component there. So, but my focus is more about like the correction of the data they develop to help to understand the path of the light, and then correct the path, and then allow the telescope to see more clear. Yeah, that's what I learned.
What did you love about this talk?
I think it's very, to me, it's very clear and also very interesting to explain the theory behind. I understand it easily. Also, I also have an engineering background, probably. But I think it's clear because the idea to me, though I'm not in the same view, but to me it's very clear. It just helps you to see more, better. Yeah, that's cool.
No,
No, he said everything?
I just think that Sky News is trying to be the new bird with their star.
Yeah.
So it's very fancy.
Okay, yeah, very perfect. Thank you guys. That was very nice. Cool. Yeah, we collect everything there. Okay, good. Nice. So now next speaker is Tim. Tim has a face, believe me, he's there. And he will talk about impact of intestinal cancer genes on immune cells. And his background is biology. And right now he's a PhD candidate at the TU Munich. And interesting to know about him is that he said that since he once dreamt about a unicorn, every time he winks, he sees glitter. So I'm a bit jealous, I have to say. But yeah, okay. So we're gonna switch the presentation. And Marita is drawing the next two names. Thank you.
So the artist in prop for the next talk is Silvioli Ricarda. Here. Perfect. Thank you. And the second one, I cannot really read it. It looks like a D with two eyes.
Or do? Is it, you have to talk? Yeah?
No.
Are you?
Perfect.
Okay, great.
Thank you.
Okay. All right. Then, I guess we prepared. Improv artist is set, yeah? And time is there. And Tim is ready. Are you ready? No?
But I can start.
Yeah, we can't sing them. Okay, so give an applause to Tim and the stage is yours.
Thank you. So my name is already mentioned, that's also my background. So today I want to talk about the impact of intestinal cancer causing genes on the immune system. Starting with very simple genes. Also cancer was perceived very simple in the beginning. So is it not on? I think I switched it on.
It doesn't go on way over time, so. It's on. Yeah, it should be on. Maybe. Yeah? It should be working. Maybe we can. Maybe it's just behind your. Okay. You can start. Continue. Yeah.
Okay.
It's better.
Okay, let's make it very, very strange. I just hold it in front of my mouth.
Want to use this one?
Yes.
Yes. All right. Problem solved.
Should be good. Okay, now I can start the rep period with this microphone. So we have like a very simple view of the cancer. So we have like a cancer cell, and we have like a cancer cell because it has like cancer genes which are activated. And these genes are leading that the cancer cells becomes more, it's proliferating. Becomes 2 cells, 4 cells, 8 cells, 16 cells until the patient dies. However, like as finally you get all the money, if you're related. However, nowadays cancer is like considered to be a little bit more complicated. So we have like a lot of cells in the surrounding, and the cancer cells are not only proliferating but also communicating with these cells. And this communication is also influenced again by cancer genes. So this is something highly interesting, and we want to study it by using mouse models. So this is a mouse, it's not a kangaroo. And basically these mice are genetically altered, so they have like new DNA. And what's new is that they have like a William promoter and a Career recombinase. And before I talk loud, let me explain it to you. So the William promoter is simply a DNA sequence where only in the intestine certain proteins will bind, and therefore enable only the intestine that the polymerase will bind, which is like the reader for the DNA. Therefore, the polymerase can read the DNA code for the Career recombinase, enabling it to become protein. And the Career recombinase is a protein which is like a molecular scissor, again recognizing DNA elements. And therefore, this Career recombinase will only cut out the intestine because only there it's like given. For example, a stop signal in front of an oncogene, a gene which upon activation can cause cancer. Or reverse, it can cut out a tumor suppressor gene, a gene which normally protects from cancer. So these mice will all get tumors. Yes. And we want to study them. And for example, it was shown that tumor cells can secrete a protein called CCL4. And what CCL4 does, it attracts immune cells, and the immune cells can then attack the cancer cells. But for example, oncogene was shown that it basically blocks the secretion of CCL4. And to find out if maybe less or more immune cells are given in our models, we want to simply cut our frozen tumors. We will have a very thin tissue layer. We put it onto a glass slide, and we show antibodies on them. So antibodies are highly specific. They will label just very specific immune cell types. And then we will have a light signal, and we will see on this spot, there's this antibody, and therefore this type of immune cell. The next step is that every cell has proteins, and every cell will present cleaved proteins or cleaved peptides on its surface, which enables the immune system to recognize them and to kill the cell. But the cell can also express inhibitory proteins. For example, PD-L1, therefore the T cell will not attack it anymore. And we want to look if the mRNA is increased in these tumors. So the mRNA is between the DNA and the protein level, be a protection or mechanism against the immune system. So therefore, is this okay? I'm just irritated by this concept. And the last step is that we want to also see if the immune cells really have an effect. And this we can only see if we implant or transplant cancer cells into immune deficient mice and see if they maybe will have a worse survival than simply normal mice. And what we finally want to do is that we, of course, want to find out new mechanism how really a cancer cell is interacting with its environment, with the cell surrounding it. And therefore, maybe there are new possibilities also for treatment. So the patients will die later. So you will get money later. That's another topic. And finally happen basically these guys, so the medics. I think I'm ill in time, but I was completely irritated with this time. But that was it already.
You get extra time, don't worry. That was technical. Don't worry. And thanks for not being irritated and stressed by technical issues.
I think that, yeah, everyone is confused. It's not irritated.
Okay, right.
The master student told me.
I see. Okay. Well, thanks a lot for that. Okay. Great. So you know what to do. Grab your phones and rate Tim's talk, and this gives a little bit more time to our artists to draw, and for our improv speaker to still think about what to say. So I'm gonna switch. Ah, there's Okay, interesting. Okay, so choose Tim's name, rate how much you like the talk between 0 and 9. Oh yeah, that's really still music. Okay, this is you. Now? Okay. And yeah, so we wait. Ah, you're already done. Perfect. Great. So come on stage. Perfect. So what was your name again?
Ricardo.
Ricardo, hi. So we have you, and where is our speaker? He's there. Victim, not a victim. It's an opportunity, right? To share.
I'm the victim of me.
Okay, yeah, that's
On my
okay.
growing, though.
That
My
maybe, yeah. Hi. So maybe you should. Well, let's do it here this time so that people here also see something, right? That's
You can
here.
do it.
So, what was your name again? Leanne? Okay, so could be fine. Sorry. Okay, so summarize the talk in your own words using slides and tell us what the talk in general was about. One thing that you have learned from the talk and some things that you've loved about Tim's talk, okay? All right.
So the cancer cells, they have cancer genes. When they activate it, they can lose their space and then can produce certain cells, then like cause more and more cells. So the patients will eventually die.
You agree?
I think basically that's it. I think it's pretty clear, like how the cells proliferate internally.
Okay. Do you have anything to add?
Yeah.
Anything that you've drawn? Anything to add? That you
I
didn't
don't
say?
want to show you this to anyone anymore.
Maybe Tim wants to keep it for later.
Yeah.
Yeah? Okay, so you can just like collect it and people can collect it. So yeah, thanks. Thank you so much. All right. Okay, so next talk will be by Maria. Maria will talk about the effects of mindfulness meditation on the brain. Yeah, that's okay. So she has a background where she has a bachelor in mechatronic engineering from Mexico, a master in biomedical engineering from Canada, and now she is in Germany doing her PhD at the Medical Life Sciences and Technology Faculty of the TU Munich or Center. What is it? Center. Center. All right, center. And she had a chicken as a pet. So, but you didn't eat. Okay, you didn't eat. I wanted to ask a question. Okay, good. Okay, so your talk is on your computer or? Yes. All right. So while we do this, I hand over to Marita to have the two new improv speakers and artists. Thank you.
So the first artist improv speaker is Boaria Matsalami. Here, perfect. Thank you. You can go already to the back. And the second one for this talk will be Beat Hall. Perfect. Thank you very much. But don't look what he's drawing there because that would be cheating, right?
Thank you. No hurry. No hurry. Okay. Sophie, we see you? Yes, we see what's up there. Okay, and the microphone? Yes. Yes? Okay, magic microphone. Okay, so yeah, you're prepared? Yes, ready? All right. Then we're gonna listen to your talk, and there's the clock, and the stage is yours. Have fun.
Okay, thanks. So sorry for that introduction. You got more effort than it, but I didn't eat my chicken. And so please now stop what you're doing and watch this. Yes, your breath. Now want you to close your eyes and focus on your breathing. Feel how the air enters through your nostrils, up to your nose, and now back down to your trachea, and now how it enters into your lungs. Say it slowly, close your eyes. And now this is an exercise to remind you that you are alive, that you are here, present, in this moment. You can now open your eyes. So this was a short meditation, what we just did. Since I'm a mindfulness meditator, and I know the benefits mindfulness has introduced into my life, I wanted to show you how mindfulness can not only change your life, but also literally your brain. I'm Maria Mora, as was introduced already. I'm doing a PhD in medical restoration technology at the State University of Munich. And the previous topic of my research is investigating the effects of mindfulness meditation in the brain after a short mindfulness training. Since all the advances in neuroimaging, we can now use this technique to analyze the change and the structural and functional changes in the brain after a cognitive training. In this case, mindfulness meditation will be our cognitive training that will help us improve some aspects of our cognition, such as our attentional control, also known as executive attention. What's executive attention? This is the capacity we have to choose between what we ignore and what we pay attention to. There are three main regions in the brain that play an important role in attention, and this is the prefrontal cortex, the insula, and anterior cingulate cortex. But now we know that by several of these regions working together. This is known as a network. So there are three main networks related to attention. These are the central executive network, the default mode network, and the failures network. The central executive network is also known as the stay on task mode, and this is the one that is done when we are focused on performing something. For example, reading a book or the daydreaming. Given the nature of these two networks, they cannot be on at the same time. That's why we need another network that mediates the shifting between these two. And this is the failure network. Interestingly, two main brain regions of the failure network are the anterior cingulate cortex and the insula. And this is the network we'll be training while performing mindfulness meditation. This leads to our first research question. Is there an improvement in our control of attention after a short mindfulness meditation training? To address this question, we'll use a full technique called functional MRI. This is a method that enables us to detect the areas in the brain that are active while performing a specific task. In this case, we test the attention of our participants. And we expect to see an increase in activity in anterior cingulate cortex that goes along with an improvement in their attentional control. We also have a second research question. Are there changes in the structural connectivity between the anterior cingulate cortex and the insula? To answer this question, we use also a super good technique that is called diffusion system imaging. And with this method, we can create representations of the white matter tracts of the brain. Here are some examples of our white matter tracts. So, the research I'm conducting consists of 50 participants divided into two groups. One was control and the other experimental. The experimental group underwent web-based mindfulness intervention for 31 days, and they had to meditate 15 minutes every day. The control group also worked their attention every day for 15 minutes while learning about topics related to how to put their health or well-being. This was a blind sided study, which means that they didn't know one-sided study, which means that they didn't know to which group they belong. The participants were scanned after and before the training, and well, we are just waiting to analyze it.
also like the internet project. We can talk later. All right, so you know what to do. Grab your phones and break Maria's talk. So, wait, I'm gonna switch screen again. All right. Oh, cool. We're getting faster with our intro talks. Hi. You're already coming at the same time. That's good. So, what was your name again, please?
Julia.
Julia. Hi. And your name is? Eve. Hi, Eve. Maybe you want to, like, I don't know, go somewhere here with the drawing because I guess it's easier if the projector is not. It's more to there. Yes, I think. Is that good for most of the people, I hope? Yeah? Okay. So you can look at it for a second. And then give us a summary in your own words and tell us what the talk was about. Say maybe one thing that was really new for you that you've learned and what you loved about the talk. Okay. And you can, of course, jump in. And if you forget something, funny, like.
Okay, thank you. I will try to use the tools for outward. The talk was about meditation, of course, and how meditation can enlighten us. And what we learned today is that when we talk about our brain, we have two networks which are basically working like antagonists. So the one, I'm not completely sure on which side, but the one is the one which is more for the executive task. So it means when we actually have to do something or focus. Whereas the other one is like basically default mode when you sleep. So, and they can't work at the same time, but we can use meditation in order to find something like a central stage. I'm not completely sure about this part, but what we have heard is that there's a lot of research going on how meditation can, or if you are more focused afterwards, maybe. Yeah, I hope I used your artwork
I
nicely.
think I made a mistake between turn off and on sign again. The second is not closed and closed, so that was why we were in a hurry, but yes.
So, I like, before the talk, I mean, since she's a trained meditational teacher, if I get it right, or a meditationalist, I like the way she talked around. Thank you. I liked it really much. I could focus, and it was a nice rhythm of talking. Thank you. And what I learned is that, yeah, maybe I should start meditating.
Great job, guys. Thanks a lot. All right. So we have the last talk before the break and before you can go more here, but I hope you're gonna stay focused for Andre's talk. Hi, that's Andre. Hi.
Hi, that's me, guys.
Yeah.
Double Andre here.
Are you gonna rap now?
You hear me well? Because I'm talking loud, or it's microphone?
I think we should open it.
All right.
Okay, so Andre is gonna talk about awesome, right? And his background is in electrical and computer engineering, and currently he's a PhD candidate at the Chair for Biological and Imaging at the TU Munich. And his passion is taking pictures. You will hear more about that, I think.
Right, that's cool.
Very excited. Yeah. All right. So where is your presentation? Tell me, please. Is it on the
I think mine was.
While they're doing this, we are going to have the next names for the improv talk. So the artist for this talk will be Bot School. Where is he? Thank you. And the second one will be Georgia Giacopoulou. Sorry if I pronounced it wrong. Thank you very much.
Okay. And left and right is right. Okay. Okay, wait. Give us a second. Sorry. Yeah, back forward. Okay, wait a second. It's always a bit stressful if it's working or not. Okay, so Andre, You ready?
Yeah, I'm ready.
Yeah, you ready?
I always wanted to be ready.
Oh, well. We expect a lot. Okay. So, the stage is yours.
All right. Hello, everyone. Some of you, of course, can say, well, that's weird. Well, that's not weird at all. And here, I will try to tell you why. So, I'm a PhD student at Technical University of Munich, and I work on the development of an awesome technique which we call ARSAM. And we use this technique to image human skin in biological and medical applications. The first question usually be asked, why skin? Well, did you know that skin is the largest organ of the human body? Also, it has very complex multilayered structure. It consists of many appendages and skin components such as hair, subcutaneous fat, microvasculature, and many more. Also, being such a complex organ, skin is affected by various diseases. Psoriasis, scleroderma, skin cancer, melanoma, you name it. I mean, some of them really deadly. Also, there is evidence that many of the, in the skin, you can find at very early stage signs of cardiovascular diseases, diabetes, or metabolic syndrome, and others. So that's why it's important to look inside the skin and to see what's really going on. Because so far there is no modality that has done it, and we are sort of the first. That's why we developed ARSAM, which stands for Rapid Scanning of Acoustic Visual System. Raster scanning of the acoustic viscosity system. Anyway, ARSAM. The system is based on the optoacoustic effect. So basically, in a nutshell, we shine the light inside the tissue, and then what happens? Molecules start to produce the ultrasound. And what we do? Of course, we listen to what they say. And they tell us a lot about themselves. First of all, they tell where they are and how superficial or deep they are. They tell us about how big or small the structures they compose. And moreover, they tell what they are, what kind of molecules they are. So, and using all of this information, we take the pictures of the skin. And at this point, some of you may wonder, so how does my skin look like? And here's an example. What you see here is a very, not bad, but anyway, what you should see, and you see here is the dense microvascular network. Also in green, you see the smallest capillaries, the smallest vessels in human body that are used to deliver the nutrition and oxygen to the tissue. All right, so blood. The main component of blood is hemoglobin. Hemoglobin can be with oxygen and without oxygen. And from this, you can extract very important parameters such as oxygenation of blood, which is used a lot in the medical field. And how do we do that? We use just different colors. We shine the light inside the skin at different colors. Let's say we use one color here, we shine this inside the skin, and then hemoglobin that has no oxygen, it starts to be the loudest. It screams out loud, hey, I'm hemoglobin and I have no oxygen whatsoever. Cool. Well, using different colors, we see this picture, which is oxygenated hemoglobin. It has oxygen, and it tells us, well, now look at me, and I have the oxygen. I'm so cool here. Anyway, but the skin is much more. Skin has many other structures, right? So what else can we see with awesome ARSAM? And that's what we see, this melanin. This is the melanin layer. Melanin layer is in the constant, melanin itself is a pigment, which is in constant battle with the sun. Sun basically tries to kill us all the time, and melanin basically protects us, our guardian, and it doesn't allow the sun to destroy our body. Also, the color of the hair is basically also melanin. It's what defines the color of the hair. What else we see? Lipids. The winter is coming, it's going to go on, but also awesome because you can see, right? But the subcutaneous fat, it keeps insulation, it keeps us warm at night and happy. Or sebaceous glands, they make our skin also soft and nice to touch. Well, also kind of important. For water, we are mostly water, and that's what we see in epidermis over here. That's this technique, ARSAM, provides us all of this information at once. So we retrieve morphological information, we also retrieve functional information, and with all of that, our main goal is to move the system, translate the system from the lab into the clinical bag. And that's what we do. We are basically trying in a very tight cooperation with medical doctors and biologists to find the biomarkers that are attributed to different diseases, and based on these biomarkers, maybe diagnose diseases earlier or even help to treat them. So that's our main goal. And I hope you enjoy the talk. Be sound and take care of your skin.
Thanks so much. All right. Cool. Guys, you know what to do. You have to rate now Andre's talk. Grab your phones. Okay, so it's working. Very happy that technique is working so far. All right, so go and do your votes. Say how much you liked it. Yes. In the break, we have a break right now, right? So this is the time where you should ask questions and discuss, right? Okay, and also afterwards and after. Yeah. Okay. So please do the rating and artist is ready already. So and also our improv speaker. So let's proceed. Okay, so this will be the last improv round for this round. Hi. What was your name? Dimitri. Hi, and Georgia. Hi. Okay, so maybe take this position again. And that's wow. Are you an artist or is that no? That's weird. Yeah. Okay, so Georgia, now summarize in your own words what the talk in general was about, one thing that you have learned, and what you loved about the talk, using this very beautiful slide. Yeah.
So the talk was about awesome, which is an awesome technique in order to take images from the skin. And here this is the skin, and this is composed of many layers, and it includes many molecules. So the point is that there are many diseases which are related to what molecules are in our skin. And the point is that with this technique we can see exactly by detecting some ultrasounds which molecules are there. So again, you can have some biomarkers and then use them in order to see some.
And one thing that you loved about the talk, maybe, or
It was really not in order for me to
do you have anything to add, Steve? Or
I think that went well.
yeah. Okay. So Nick is really holding his hands like he's like I don't know. Can you still move your hands? Shake them maybe a bit? Okay. No, seriously, like it's fun to see that. Okay, well, so this was end of round one. So what are we gonna do now? Time for a break. So there should hopefully still be a few drinks and beers left. Correct? No? Everything empty? I hope that wasn't like it. Well, get up, get some air and talk to each other, ask all the questions you want to ask, and in 15 minutes we resume, alright? Thank you guys.
My background is computer science, so it's related to nature and biology. And we can try what's related to biology.
Becky explained like why she was using the name. But then I then she said, yeah.
So for any latecomers, if you still want the Wi-Fi password lowercase here, right? So remember that? You can still log into the Wi-Fi if you still want to. And yeah, so I hope you had a great break. You had a lot of talks. It was really tough to bring it back. So we have half an hour break now. So good job communicating. Thank you. That worked well. But continue that please afterwards. Okay, so just one remark. I know there was not a lot of pizza, but at the after party at Strabula Bar, they have food until 12. So you should not be scared to start, okay? So there is food. Okay. So we continue now. We go into the second round. We have another five-minute talks. And our very first speaker. I'm sorry. That's what I meant, of course. And I should have known because he says he cooks the best and the most amazing lasagna. So that's strong hint. Yeah? And yeah, in his first car was a Peugeot 107. So if anybody has the same car as the first car, you can talk to him and the French. Okay. Okay, so while we prepare your presentation, I hand over to Marita to know who will the next improv artist and speaker. Thank you, Alex.
So, for the next talk, the artist improv will be Katrin Lemle. Where is she? And the second one will be Raul.
Can you hear me? Yeah.
Okay, good. So,
Sure.
okay. Antonio, you ready?
Yes.
Yeah, good. So, have a lot of fun and yeah, the stage is yours.
Thanks. Good evening. Today, I'd like to start with a question. How do we improve our ability to understand biological complex phenomena like cancer, especially in humans? Let's hear what this humble petri dish has to say. A petri dish is a transparent dish and complex three-dimensional tissue. But what will it mean? Every patient is different, and thus every cancer, which exhibits various mutations, different microenvironments, and also different responses to drugs. Traditionally, to study the complexity of cancer, appropriate model systems are necessary. So far, in vitro 2D cell culture and mouse models have been considered the pillars of preclinical evaluation of different new therapeutics in all branches of biomedical research, but they still suffer from some limitations. 2D cell culture is disadvantaged because due to its culture condition on a plastic substrate, and it is unable to mimic in vivo situations. On the other hand, mouse models are time and cost consuming, and one might argue that do not generalize perfectly patients. And finally, human tissue has a limited availability, and it is difficult to manipulate. But if we want to understand cancer, we must be able to create and to grow it in a lab. We are not in Alice in Wonderland, but it is already starting to begin, and it is happening in many laboratories worldwide. It is considered a breakthrough for cancer treatment, and I'm talking about mini organs in a dish or organoids. Organoids are a group of cells in laboratories that you can grow in three-dimensional structures. They contain multiple cellular types of the in vivo, small fragments of every tissue of our body, like intestine, pancreas, and lung, and many others. But researchers have also started to grow organoids from cancer patients, from human cancer patients. And this is exactly what I'm doing now for my PhD. we take biopsies from colorectal cancer patients. We isolate tumor stem cells from the bad tumor, and we immediately embed them in a scaffold that we will call extracellular matrix. Extracellular matrix. And then, like this, you can be able to expand them and to in a three-dimensional structure. And finally, we want to assure if the patient-derived organoids resemble both genetically and histologically the primary tumor. So, organoids can be considered as a bridge between 2D in vitro models and in vivo models, but they have also potential in clinical aspects, not only for cancer modeling, but also for biobanking, regenerative medicine, and to test efficacy and toxicity of drugs, and for precision medicine. We are still at the beginning of this new revolution, but with time, we will get more accurate models for resembling human physiology. Thank you very much for your attention.
Thanks a lot. And you know what you have to do. Thanks a lot. Again, music, sorry. Well, can also listen to music in the meantime. Okay, and we already have your improv artist here. Great. Okay. So, while you are still raising his talk, and I hope you can spare one ear and one eye at least for, can I ask for your name? Katrin. And where was your name again?
Rahul.
Rahul. Okay, Rahul and Katrin will present and summarize Antonio's talk now. So tell us what the talk was about in general, maybe one thing that was new for you that you have learned, and what you really liked about his talk. And of course, if he forgets to mention something on your poster, you're allowed to interrupt, right? Okay.
Thank you. Good evening, everyone. Like Katrin has done a really good drawing that I guess summarizes everything from the beginning to end. So initial cultures that was done was mostly on Petri dish, and things were mostly two-dimensional, which I understood from the top. And what he's doing is he's trying to analyze things more in 3D environment. So that's why there's a 3D structure and a different methodology of doing the culture that helps more growth in the 3D atmosphere and helps him to analyze things and study them in a different environment and look from a very different dimension. And this not just helps him to understand the real cases which are related to humans, but it also helps him to analyze cases on how effective the drugs are going to be. I really was a little fascinated about understanding that, until now we were doing things only on 2 dimensions. Okay. This is really part of it. And when he said future, I was like, oh, this is going to be an automotive talk, but it was something else. It was exciting though.
So did you forget anything? No. Are you also a biologist?
Yeah.
All right. Okay. Well, thank you. Thanks a lot, guys. Thanks, Antonio. And yeah, we go on for our next talk. So, this next talk will be by Rachel. Hello, Rachel. She will tell us about entraining the brain. And her background is in neuroscience. And currently, she's a PhD candidate at the Medical Life Science and Technology Institute. What did we say? No? You did? All right. Okay, great. Cool. Well, great. Thank you, guys. That was very interesting. Okay, and then let's go on to the next talk, which will be by Alicia. I'm very happy to have her here because she's a master's student. She's not a PhD student for now, so this is a nice change. So thanks for being here. And by the way, I was asked beforehand if only PhD students are allowed to participate. Of course not, but somehow they seem to be the people who want to interact and to communicate and to get free beer and pizza or something like that. I don't know. But everybody, of course, is invited to present his or her science, right? Okay. So, Alicia will talk about the sneaky little ninja. So, be curious. And she has a background in biology and currently also does her master's in biology at the LMU. And she told me that she is actually an adrenaline junkie. We need some Mac help. Yeah, again. What do we need? This? Okay, great. Okay, so Alicia is an adrenaline junkie, she said. So she does bungee jumping. So did you really do that? Oh my God. And canyoning and riding safaris. So yeah, I'm impressed. Okay, so and when we prepare this presentation, I hand over. Thank you.
So for the next talk, the artist principal will be Gülşah. Thank you. You can go already to the back. And the next one is also a girl, so I guess we have this time the first round. There are two women presenting it. It's Vilma Trick. Where is it? There. Hi. Thank you.
Okay, so are you ready? Yeah. Good. Then the next 5 minutes on stage are yours, and I hope you have a lot of fun.
Hi, I'm Alicia, and as Alex already said, I'm a master's student at LMU. I'm studying biology, and currently I'm conducting my master's thesis in the field of innate immunology. So we are interested in our immune system, and we are specifically investigating why our body defends specifically viruses and bacteria. But to break it down and make it a bit simple, I gotta tell you the story about the sneaky little ninja today. The sneaky little ninja is very, very small. We cannot see it with our eyes, and it is super tricky. It can attack our body without our notice, and it is everywhere. It's everywhere in our surroundings. It's in the air, it's on door handles, it's just everywhere, and it is always ready to seize us. I mean, who doesn't like a place that's warm and it has free food, right? But well, our body doesn't really like it. We're just sick. We are suffering, we have pain, and in the worst case, it can even lead to death. That's why nature developed a weapon against the sneaky little ninja. It's called suggesting defense. This weapon constantly screens our cells if there's any danger for us. And most of the time, this weapon is successful, and it can find a ninja. But what's happening once it found a ninja? Lots of signaling sounds. Looks pretty confusing, huh? So that's why I want to explain it in a bit more simple way. We have this scenario. We have a passenger in the street which spots the little ninja. And it instantly recognizes, wow, we have a problem here. So it calls the emergency center to get some help. The emergency center then calls the police and sends the little police officers to catch and arrest the little ninja. Wow, but it's good. So the danger is away. But in ourselves, we don't have little people, right? But we have molecules, and we have a lot of them. We have them in different sizes and different shapes, and all of them have different functions. And they will like similar as in this scenario I told before. So we have our passenger molecule, which is there to specifically recognize ninjas in our cells. Once this passenger molecule recognizes the ninja, it signals to the emergency sensor molecule, well, I found ninjas, we have a problem. This emergency sensor molecule is just there to spread the message. And it collects all these little police officer molecules to fight the little ninja, and this works in the way that we can think. We get fever, pain, just any way to make it really uncomfortable for the ninja in order to make it bleed. But well, how do these molecules communicate with each other? I mean, they are just molecules, right? That's where our research takes place. I name it the ubiquitin call. Ubiquitin is another small molecule in our cells, and we have really much of them everywhere. And today I show it as Lego bricks. Once the first molecule sends the little ninja, it fills up a chain of Lego bricks until it reaches the emergency protein to tell it, well, we have a problem. The emergency protein sends those other chain of blue Lego bricks to collect the police officer molecules around it in order to tell them that they have to defend our body. Well, but how does the next molecule know what the specific message is? The message is defined in the color and in the size of the Lego bricks. So here, the red medium-sized Lego bricks mean that there are ninjas in our cells and our body has to do something. And then the next molecule will have blue Lego bricks, and the specific message of the blue Lego bricks is, well, police officer molecules come and help us. But why research on this when it sounds that easy? And we are looking on the specific molecules which defend our bodies against the ninjas, and we are looking which size and color they are using to communicate with each other. Thank you for your attention.
Very nice. Super nice talk. Okay, so you can sit down. You're out of okay, so, and you guys know what to do. Grab your phones, do the voting. We already have the improv speaker coming on stage. Hi. Wow. You're faster. Wow. Okay. Lego is also on there. Really cool. I'm really impressed by all the posters. So I really think that the speakers should take them home and use them for the next, I don't know, conference maybe? Yeah, why not? I mean, this definitely grabs attention, right? Okay, so what was your name again, please? Grisha. Grisha, hi, and you were? Vilma. Vilma, hi. Okay, so two girls here explaining about what Alicia was telling us. So please, in your own words, using this nice slide and this nice poster, what the talk was about. Something maybe you have learned?
So, yeah, I think the main message is basically that if you get attacked by ninjas, you should put Lego bricks on the floor. So I think that's basically the main message, but there were more details in between. So, like, we appear to be constantly attacked by little ninjas that we don't recognize, like, I guess, so I'm not a biologist, like bacteria and viruses, I think. And the reaction of our body to make it uncomfortable for these little ninjas is by making a stick, this reaction with fever. And I think the important thing with this hole that happens in our body when we get attacked by the ninjas, there's one molecule that recognizes that we get attacked. This one builds then a Lego chain to the emergency center, which is drawn here. And the emergency center is building another kind of Lego bridge. And then the police molecules accumulate around it, and then they can attack the ninjas. And the important thing is, and the research project of Alicia is to learn what kind of Lego bricks, what are their colors, their sizes, what are the messages, and how do they communicate with each other. was very clearly explained, so I could actually understand that.
Good. Anything to add? Okay. Yeah. Cool. Great. Cool. Thanks a lot for being so brave. Thank you. All right. So, only 2 more talks to go. So, the next talk will be by Jose. Jose, I never like. Yeah, Jose Maria. Okay, right. Cool. Said it correctly. I should know he's a colleague of mine. So, he will tell us about why do we look at the brain to know what we'll do. So, he has a bachelor in biochemistry. He has a master in neuroscience. And currently, as I said, he is a co-worker also at the Max Planck Institute of Neurobiology, also doing his PhD. And he said that he actually traveled to Russia, which I assume is this image here. Yeah. And he did not die of being like so cold, even though he's Spanish. So wow. And he also said he trained a turtle to wear shoes. He has an image of that I didn't put here. But if you're interested in like how this looks like, I'm sure he has the image with him. So you can ask him about that. Okay. And while we prepare the presentation, I hand over to Malika. Thank you.
So the next improved artist will be Marta. Where is Marta? Here. Thank you. You can go already to the back. And her other part will be Philip Roth.
Oh, yeah.
Thank you.
All right. So, Jose Maria, you're ready. You're ready. So yeah, you have 5 minutes, and you want to put this in your pocket maybe, then you don't be annoyed. Yeah. Okay. So yeah, as I said, 5 minutes. Enjoy the time, have a lot of fun, and the stage is yours.
Okay, so good evening, everybody. I can see that it's already 9 almost p.m. And we are all here. Why are you here? Like every other day, probably you could be having your dinner, you could be taking a walk, you could be maybe watching some series in Netflix, and yet here you are, right? Listening to me or pretending you do. And well, I'm Jose Maria indeed, and I'm starting a PhD in neuroscience because I want to understand why you decided to do what you're doing now. Let's talk a little more about decisions. We neuroscientists say that behavioral decisions are those that imply a choice between several behaviors to do something. Like for example, having dinner, take a walk, to watch a series, whatever. Everything to do something, any verb is a behavior. And then there is all this pool of behaviors, and we have to pick up one. How do we pick up one? Generally, we are based on stimuli, external stimuli. For example, the pizza that was here before, or how beautiful Marienplatz is now in the center of Munich, or just the attractive catalog of Netflix, whoever has it. And yeah, so depending on those external stimuli, we will have several things to do, and we can take several behavioral decisions. Is that the whole thing? No, obviously no. Anyone that has all those stimuli know that also our internal state, how we feel at any moment, is very important. For example, a moment ago, you were terribly hungry, you had pizza there, so obviously you jump like this over it and finish it all in a moment. That was the decision of having dinner. Now, the nice thing of this model is that supposedly if we look at it, if we look how those external stimuli and internal state are balanced, we can understand how behavioral decisions are taken. And that will get us closer to understand why we do what we do. Is that so? So I mean, it's never that easy. The problem here is that as anyone can check just looking around, we cannot know what people are thinking. This is like a black box in ourselves. We don't know what is in our mind. We can just see that there are several external stimuli, and then we take some decisions. How can we solve that? Well, neuroscientists believe that the way to do this is to look at the brain. Because the brain is a very cool organ. Actually, it's the one that takes all the sensory stimuli, all these external things that are happening around us, process them somehow, and then elaborate a motor output, some movement that's the behavior. And the very cool thing is that the activity of the brain changes when there are representations of the computations of the brain that we can actually measure and get good images like this. It will be in parts of the brain that are activated during decision taking. For the externally guided decision and internally guided decision. The thing is that doing this kind of maps, we can get very nice maps of all the different brain areas that are activated at any time. And then we get this very good model. Sensory inputs activate brain areas involved in decision making, and then we get the motor output or behavior. Great. Seeing a picture of the brain, and then we are supposed to understand something. I mean, this is precisely the reason why I was really considering abandoning neuroscience until I met Emily Macer, who is my supervisor now. Fortunately, she has designed this super cool machine that can actually record the brain, the activity of the brain, like in real life. I don't know if you can imagine how cool this is. Like, whatever you do, whatever behavioral activity, whatever behavioral test that you imagine, you're going to have automatically the activity of the brain at any moment. And that means that you can make instantaneous correlation. You can see what is activated at any instant. You can see what is activating any other thing. You can get the whole map with all the orders, and then to really get deeper into that. That's an incredible tool. This didn't exist just 5 years ago, and that's now an door open for us to really explore behavioral decisions. So answering to my initial question, I have no idea what you are doing here or why you care about what I'm saying, but I hope that in the years of my PhD and using this very cool technology, I will be able to discover it. So thank you for your attention.
All right. Can go with the microphone? Yeah, exactly. That's the whole part of here. And you're ready here? Yeah. That was quick. Okay. Hello. Oh, that is really nice. So I have to say that with the small compounder that Martha behind poster here, she is in our coordination office in the institute. So that was not like we didn't choose your name on purpose, right? I think. So it's very cool. Okay, so what was your name again? Okay, so explain us what his talk was in general about. One thing you learned that was cool, and one thing that you really liked about his talk. And as usual, interrupt, right?
Yeah. Hello, good evening. So Jose in general talked about why and how we make decisions, basically. So first question is why are we even here? Sitting listening to his talk. And other examples are, for example, why do we go for dinner? Why do we go for a talk? Or why do we for a walk? And why do we watch Netflix series? And in the end, he told us that all those decisions are based on external stimuli and also internal states. For example, if you're hungry, you're rather more likely to go for pizza. And then in the next step, he tried to understand how exactly those connections work between the inputs and the outputs in the end, connections in your brain. And he presented a new kind of device, which he will use during his PhD to investigate those connections in the brain. That's basically what I learned from the talk. You're happy with it? Yeah?
Black box is not black because there's no black marking.
That's the black box design, yeah. And what I really liked about your talk, it's an interesting topic, and I think it was really nice that you were enthusiastic about your topic, and that made it easier to listen to you, and it was nice to hear. Thanks.
Thanks for the feedback. And this brings us to the final talk of tonight. That will be, is your presentation on there?
Yeah.
Yes? Okay, thanks for your help, by the way. Okay, so also, we have Jose number 2. and he will talk about the quantum nature of space and time. So he currently is doing his master's, finishing up the master's
Finishing
thesis.
up,
Yeah. Soon to be PhD, right? Is that that? Yeah. And it was tough to get any fun facts from him. So that's why he likes, I'm not singing, pina colada, and getting caught in the rain. No, nobody wants that. No. Okay, well, I mean, you can.
No, it's fine. I'm also not into yoga.
You're not?
No. So, of course.
Slow down. We need to improv speakers first, and then you can start.
So the first improv artist today for this talk is Anna Turbanova. Where is she? Okay. Thank you very much. And the second one will be Beulah Bauer.
Wait.
Bella Bauer, sorry. Sorry. Thank you very much.
Thank you. Yeah. You tried to really scribble your name, that we can't read it, right? It's very hard, but we found you. I'm sorry. Okay, so are you ready?
Yeah.
The final 5 minutes per night. Use them wisely and have a lot of fun. And the stage is yours.
Yeah, so as I was saying, my esteemed colleague just before said that he doesn't know why you are here. And this is actually a very good point because it is late, you're probably tired. So I think that I should start by saying thank you very much for keeping with us. It's amazing, you guys are amazing. Now, I would like to start this talk by saying that I do believe that physics, which is what I'm going to talk about today, is in some sense a kind of philosophy. Meaning that in the end, after all the abstract mathematics, we should say something about the world. Now, I know that knowing something about the world is something that we human beings want to do and that we like. But sometimes, because of all this abstract mathematics, we just don't understand what's going on. So what I'd like to do today, and since I'm studying physics, what I'd like to do today is to bring to you an idea of how we physicists think the small scale structure of the universe, of space and time, might look like. So my name is Jose. I am finishing the master's thesis in classical mathematical physics, and today, in 5 minutes, you'll be under it. We're going to go through general relativity, quantum mechanics, and quantum spacetime. So, this talk, the physics talk, must have an Einstein peak. There he is. Einstein means gravity, and we've known for some time how gravity works, right? So gravity is about taking some object and putting it in the air and letting it fall. And we know that it goes to the ground. Well, this is what I thought about gravity for a long time, until a guy that was very insightful came along. That's this guy. And this I realized that there was a lot more about gravity. It's not just an abstract force. Gravity, for Einstein, is actually about a geometrical property of the universe. So for Einstein, what's actually going on is that the universe is something like either a ball, a sphere, or a donut, or if you're from Munich, you might think that the universe is something like a pretzel. And the idea is that what's actually going on, you can describe gravity by imagining that you're like ants on a surface, on a flat surface. These ants are just going straight on. Well, the surface is flat, so they just go straight on, and they just move in a straight line. What happens, though, if you put some massive object on the surface? It's going to deform the surface. And since the surface is deformed, the same ants that just were walking on a straight line will curve without knowing it, because the surface itself is straight. So for Einstein, the big realization of Einstein was that you could describe something like orbitation of planets around the star by the geometrical properties of spacetime. Not only this, spacetime itself is a physical object with dynamics that interacts with matter, which means that space and time is something as real, as manipulatable as a water bottle or as a football ball that you can kick. This is the first important question, and it's around because it has a battery on the face. What do? You make the cat very small, put it inside a box. When you take the cat outside of the box, this is what you see. You will find out that, in truth, you cannot actually measure, you cannot predict what is happening to the battery. The battery is depleting, And when you take it out, it's going to have some value, either half full or even less full or completely empty. And you cannot predict which one of them is, even if you know anything about the vacuum. And not only that, compared to the classical case, you expect some continuous property of the world, to be actually discrete. So things that we think take every possible value from 0 to 100%, let's say, actually have discrete values. And it's just that you're looking too far away, so it actually looks very continuous. That's that. So the two lessons from quantum mechanics are these. Things that we think are continuous classically in the big scales are actually discrete. And the cats, or the physical objects, in truth exist on a superposition of states. This is how we physicists describe that you cannot really predict what's going on with the cat. Well, this is incentive, so this is enough. So this is 2 minutes, almost 5 minutes for quantum mechanics and general relativity. Now we go to quantum spacetime. There's something called spin phones. It's one of the theories, you have many more. And spin phones is a model for spacetime that thinks of spacetime using a very interesting object. That object is the quantum tetrahedron. That it is. Now, it is a tetrahedron because it has 4 faces. Why is it quantum? Well, it is quantum because it is described by side lengths that also have discrete values. They don't take continuous values, just like the battery. They have discrete values. And what that means is that, just like the cat, the tetrahedron is described by shapes. Like this, like that, or like that, depending on the side length. And the tetrahedron itself is a superposition of tetrahedron. This implements the 2 lessons of quantum mechanics. Discrete values, superposition of physical states. To get to the classical vision of space-time that Einstein had, we call this a bubble. We go to a foam, we put these guys together, and we make a space-time. So the big novelty of this conception of space-time is that you have honestly a quantum mechanical description. And you have something like a minimal unit. You have atoms of space and time. And this is amazing because this means that, if at some point we will be able to measure stuff, we can measure things like fluctuation of areas, fluctuation of volumes. At a moment, you're measuring a very small area, and then it changes the area. And at the moment, you're measuring a very small volume, and it changes the volume. And of course, well, my time is already over. This is just a 5-minute talk, as you can imagine, but we have an after party afterwards. So I would like it a lot if you can come to me. We can discuss about this stuff. And I think to finish, I think this is something that every one of my colleagues would ask of you and agree. I would just say, please stay here. And thank you very much for listening.
Physics heavy talk for the very end. So I hope you enjoyed it. And a last time for tonight, grab your phones and do the final rating of José's talk, please. Take some time. All right. It's easy to draw then, right? You can just copy paste a lot of things, right? But that's cool. Okay. So this is Anna and Bella. I remember the name. And okay, so please describe what you were talking about, what you learned, and maybe something that you really liked about this talk. And you always allow to interrupt.
Thank you. So, first I want to mention it's a bit unfair to make the last talk a theoretical physics talk. I'm a biologist, so I had many chances to understand, but in this one I really struggled hard. I remember Einstein with sunglasses and a pile of cats. No, still I'm trying. So actually, I think we could have learned a lot. I learned that space-time is an actual thing, which is measurable, and together with quantum physics makes a donut. Well, that things are not continuous when you look closer, but have actually discrete value, which is displayed by the battery of a cat. And the last part I really failed at, so I think I gave a good summary of what we learned. on in your master's thesis, and I guess you will stick to the topic because you understand a lot. No, I'm very impressed. It was really informative, but I'm probably not the right person.
Thank you. I think you did a really great job. I mean, I feel you as also a biologist, so but thanks a lot. Okay, so these were all the talks for tonight. Please a short applause for all the speakers for giving really amazing. And now the very, very final round of feedback. So now I want you to vote for your 3 most favorite talks. So please go again to our website and press the other button that says favorite talk. And now you're allowed to vote for 3 persons, 3 talks that you really like. So do you need to be reminded maybe of the speakers? I also think so. So can you please quickly all the speakers, maybe even in like the row, huh? No, what do you mean? The intro slides, exactly. Oh, yeah, I can also go through that. Actually, that's better, yeah. That's better. Okay. But spontaneous change. All right, so I show you again. We had Ida. She talked about the deer brain, what's going on. So then next one, we had Konstantin, who talked about twinkle, twinkle, little laser shooting stars in the sky. Then we had Tim talking about the impact of intestinal cancer genes on immune cells. Then we had Maria, who talked about the effect of mindfulness meditation on the brain. Then we had Andre with his awesome. Then we had a short break. You can't vote for this one, sorry. Then the first speaker of the second round was Antonio, who talked about thinking in 3D. Then we had Rachel, who told us about how to entrain our brain. Then Alicia, who talked about the sneaky little ninja in our body. Then with Jose Maria, who talked about why do we look at the brain to know what we'll do. And Jose number 2, the quantum nature of space and time. So please, do your vote now. Vote for your factor, made you choose those 3 talks, why you chose them, that they were your favorites. And also give some feedback what they could have still improved. If there is something where you say, oh man, if they would have, like, I don't know, stripped naked on the stage, I don't know, no response. No, if they had been more clear, I don't know. Something that you feel can add some value to the talk that they gave. So please do your vote now. Okay, take your time. All right. So take your time, do your voting, and while you're doing this, I just use the time for a second and also tell you about many other things that are happening in Munich that boost scientific communication. It's not only us. There are also many, many different organizations, and these are not all, but I want to just show you what is happening out here. So for example, in every, I think it's May, we have the Pint of Science. That's a lot of fun. It means science in a bar. Professors come, you get a beer. They just in a bar tell you in a very easy and understandable way. Highly recommended. This is Europe-wide, so you should go there. Then in German, most of the time, but also very recommended, is the Science Slam. So Science Slam Germany. And it also happens very regularly, and this is a very entertaining for lay audience Science Slam. I participated myself, there was a lot of fun. So if it happens, go there, it's really cool. Then we have our friends from 15 by 4, they have actually very regular events. So once per month, they have 4 talks, each 15 minutes, that's why it's called 15 by 4. And I also highly recommend you to go there because they always have amazing speakers and also different backgrounds, so go there. And of course, on the very left, we have Soapbox Science that I also, in the back, Becky, who is it? Yeah, Becky. Talk to Becky if you want to participate there. I did this year, amazing experience. It's about, so you have women talking about their science just on the street or at the Leonsplatz, we're standing on a tiny soapbox. People really liked it. It was a lot of fun to share science and to really increase visibility of women in science and of science in general. So there was a lot of fun. I highly recommend that. And yeah, so talk to Becky if you're interested. Or to me, I can tell you a lot about that. And also, we of course always interested in changing and improving the Munich Science Lab. So if you like our idea and our mission, just talk to us because we would really like to spread this idea and together with you shape the future of the Munich Science Lab because it will never be the same. We always change things, and if you feel you have something to add and want to also spread the word, communicate with us. So that would be really great. Okay, so and now we would go to the data analysis and to the prizes, but before we do this, which is a lot of fun, I remind you of the after party, which will happen in Stragula Bar, or Stragula, I don't know how to pronounce it, which is here. So you can walk for 20 minutes, or you can take the bus until here and walk the rest, which is also roughly 20 minutes. And so they know that we are coming. There should be enough beer, hopefully. You can order food if you want, if you're still hungry. And it would be really, really nice to see some of your faces there so we can keep on discussing. And also a lot of the speakers are joining, and so you can still ask them all your questions you didn't have a chance to during the break or beforehand. So yeah, that would be really, really cool if you all joined. And he was coding constantly. I saw it. This is really amazing. Also with your the count, he has a tiny app that counts how many types he has in a second, and it was constantly blinking. So that was really cool. And is he ready?
Yes, I think so.
Cool. So I guess you're all excited about what your votes have done and what the results are. Who's the winner? Maybe we have a winner. I don't know. And also about what you rated, and maybe we get to know what a good talk makes a good talk. Maybe we have a better idea now. So let's see. Okay. Do you need an adapter? We have adapters.
Oh.
I hope. It's the right one. So give us maybe 10 seconds. This one. Always exciting.
Oh, this was one of those the last session was probably. Who here fucking loves science? It's great. It's so good. And it's ridiculous how good it is, right? It's ridiculous how fun it is. And here we are showing it yet again. We're spending our Friday night watching science talks when we spent the entire week and maybe our weekends doing science stuff. I mean, who is a PhD student? If you're a PhD student, you're in the middle or somewhere right now. You've been doing science studying and watching talks and doing lectures and being in the lab for somewhere close, if you count, in the high school, beginning of bachelor's, always to now, for at least a decade. At least 10 years you've been doing this. And you still love it. It's so great. I don't see this all the time, and I just think it's amazing. But sometimes you go to a conference and you listen to a talk and you go, oh, that wasn't that good. You know? Sometimes you spend the entire day at the conference and you listen to 80 speakers and you see a bunch of posters and you see your friend afterwards and they go, hey, how was the conference? And you go, it was okay. There was this one good one. That's terrible because we spend so much time. We love it so much. So yeah, one of the questions that we had when we decided to do the science slam was, what makes a good science talk? And I mean, I'm really teaching oriented, and I had this theory, and that was that a good science talk was one that taught science well, right? It was something that made an impact. It made a change in the listener's life. They view the world one way, and after listening to you, they view the world a different way. Which meant that when thinking about how to give talks, we shouldn't be thinking about how our talks look to us. We should be getting feedback on how our talks change the people that are listening to them. That's why we had a science slam. Our first science slam, that was the model. Okay, we thought great science talks teach science well. That was the motto. That was the model. We had it all. And so for the first two, we thought we would rate things in two ways. First, we'd ask people how engaged they were, how much they felt they were connecting with the talks, and they just had a number. And the second thing they would do is we would ask them if they learned something, the things that the speaker wanted to teach. So we'd ask each speaker to have 3 questions, and we just asked the audience if they felt like they knew the answer to those 3 things after listening to talk. They didn't have to answer the question, they just said, yes, I know the answer, no, they didn't. That's all. All right? And so we collected a bunch of data. And we're using TweetBack, so I was typing things by hand a lot. All right, this is the first science slam, the second science slam, and combining together into the third science slam. And we learned a few things. All right, one thing we learned was that the amount people said they remembered seemed to be related to how engaged they said they were. And this, in turn, related to who won the science slams. But at the same time, it also told us that people really wanted some people to win. All right, we couldn't ask that anymore. You can't say, "Hey, did you learn?" And they say, "Yeah, I learned. Sure, I learned from my best friend." But we learned a few other things. That short talks, people said they remembered a little more than long talks. I thought that was kind of neat. And that long talks, they said they were more engaged than the short talks. And that kind of matched what people were saying to us as well. So over time, we started thinking differently. We said, okay, well, wait a second. Maybe it's not just about teaching. Maybe there are other goals that people have when they're giving a science talk. Okay, that's what our science slams 3 and 4 were about. The first 3 goals we said was that these talks are rated as good by the audience if they meet the goal of being logically consistent, which meant they were kind of clear, convincing in some way. The person listened and went, aha, everything you just told me adds up to something new. Or they were novel. They said, aha, whoa, that's cool. You have changed the world. Or it was engaging. And then the next time we said, no, that was confusing to everyone. No one understood what those categories meant. We changed it to informative, persuasive, entertaining, and inspiring. Which, when doing some analysis on the data, turned out to be 2 categories: infotainment and perspiration, which was a combination of inspiring and persuasive, apparently. Didn't make up those terms. I got it from this blog article that said there were 6 goals, and I selected 4 of them because I thought they sounded right to me. Very scientific. All right? And this was the data. We started using them. And the more persuasive they were, and the more informed they were, the better people said they talked. And it became hard to figure out what was the underlying idea. Suddenly had to embrace diversity, which was good. So then we started thinking, well, maybe we got the categories wrong. Maybe there are different categories that were important. We went to Berlin last week, and we asked over so many people which categories they thought would describe a good talk. We gave them 30 of them, and they voted on the ones that they thought were good. And then we did a science slam, and they said that the ones they selected most often for the talks that they saw and the talks they thought were most interesting were these ones. They thought good talks were ones that were entertaining, passionate, interesting, exciting, clear, and well-structured. Unfortunately, when we did the analysis and we looked at the talks that were rated lowest, we also learned that the worst talks, the audience that were the worst talks, were the well-structured ones, and the clear ones. Which is why, in this science slam, well-structured and clear is a positive and a negative thing, just so I can just sort that out. Didn't make much sense, but that was the inspiration. After looking at the data, which I'm going to show you, I have there's a new thought, and it's come from a lot of discussions that Alex and I have been having over the last month. And that is that the great science talks don't have a certain set of qualities that describe the talks. It's that the speakers themselves demonstrate a set of qualities that we all value as scientists. But there's something that we love about science, and we love to see in scientists. We love to see, after doing a lot of this stuff, we love to see speakers that are explicit. I know, like explicit. What does that mean? That means clear. That means that they make a riff. They stand up and say, "Hey, I'm trying to find this. Here's my ideas. Please listen." You know, they make themselves vulnerable, and I think that's a human part of science. There are scientists that are trying to promote change on a personal level, on a global level. On a personal level, they're trying to accomplish something. They're trying to grow their understanding of the world, and they are trying to experience a new part of the world that they never could before. When they go into the lab, they're creating their own little universe. And on a global level, they're trying to change the way the world sees things. And that's something we love to see in scientists. Right? That's one of the reasons that all of us went into science. We like it when it's evidence-based. I know, it's kind of boring, evidence-based. But in a personal level, that means that we love it when people show us data and explain how they felt when they were collecting that data. What it was like to be in the lab and how they saw things. Maybe they didn't measure it, but there was something they saw, and after seeing it 1,000 times, they got something, it changed them, and they're trying to communicate that feeling. Of course, the data itself changes things too, and that helps us. The ideas that come out of that data help to change the next person as well. And finally, we love speakers that are transparent and honest, that aren't trying to sell us something, that are honestly trying to show us, to everyone, what they saw. All right, and in doing so, opening themselves up to being changed again by whoever's listening. Anyway, that's kind of where the current thinking is on that. All right, but that's not really what you want to hear. You want to hear, what your own data says, right? Let's take a look at it. All right, so this is the Munich Science Sample analysis. This is a Jupyter Notebook interface. Okay, it's being hosted on Google's Collaboratory platform. Next time we do this at JetBrains, we'll probably use JetBrains platform. They have one called DataLore. This lets you run analyses on their servers, without having to install a bunch of software. And this language is Python. So you're gonna learn a little bit of Python while you're seeing the analysis. Is that okay? Yeah. All right. We have this data. It's an Excel file. Oh, you are going to see a lot of personal data. We never show personal data, but now everyone's put comments. So your comments might appear here. Hopefully you said nice things. But let's be open, vulnerable. It's going to be fun. Okay? For example, these are the categories on the questions, and this is how the data kind of came in. All right? We had these kind of comments. And I've sorted it out into good words, bad words, and other words categories, okay? I'm running this code right now, kind of live. All right? We had a total of LenVF votes. We had a total of 1,000 votes. Wow. And if we were to just break apart all the words and just see all the words that people said when they were listening, we could find out that in total, I separated the good words from the bad words, and then I put them back together. In total, we had 6,500 words that we clicked in these 4 hours. That's amazing. That's a huge amount of data. Nature's gonna love that. I ran it like halfway through to get a sense of whether the code was working. This is how positive we were overall. In general, we liked the talks. Good job. The number of times they said the score. Apparently, I don't know what this is. Maybe we have only 9 didn't in reality. Yeah, there we go. That's so in general, we liked our talks roughly 7-ish out of 9. So that's good. 6-ish. Yeah. The most common words chosen to describe the talks out of the positive words were the talks were interesting, they were passionate, they were clear. Good job, speakers. And I've learned how to make word clouds recently, so here's a word cloud. The negative words that we use. We gotta see both sides. Let's get a sense of what happens. Which negative words do we pick most often? When forced to and then not forced to, that story changed a lot over this. We said it was complicated, dry, and not understandable. Oh, we said that a lot. How did you say that they're clear and interesting, but complicated and not understandable? Data. I'll tell you. Now, how these words relate to the actual ratings? When we said it was good, so when we liked the word, we said it was exciting. We said exciting apparently means good. If it's exciting, we're going to think it's a good talk. If it was a passionate, enlightening talk, a worrying and frightening talk, we really liked it. We should have a most frightening one.
Yes.
That's amazing.
Yeah.
Okay.
That's new.
And if we relate that to these, we like interesting, passion. And the talks we didn't like, okay, so the talks we really liked, this is different from most picks. This is the words we picked when we like interesting, passionate, clear talks. That might get us back to one of our old ones.
Yeah.
What do we say about talks we didn't like? We said it was not understandable, complicated, boring. Now it's a science lab. It's meant to be entertaining and engaging. But I bet, at least I think, that these words apply to normal science conferences too. If you keep that in mind when giving talks for your colleagues in a lab meeting, or at a conference, or at your poster, people might get a good opinion when they leave your talk. You could have picked any number of positive words and any number of negative words. How critical were we as a group? Just in total number of words. Did you prefer to take lots of positive words or lots of negative words? Did you take a lot of negative things? No. You pick lots of positive things. On the right is the number of true words, positive words we picked. On the left is the number of negative words we picked. When we saw a good talk, what did we fill in? We said, nice outro. That's a random sample. Sun kills. Straightforward, perfect, engaging, lively. Oh my gosh, these are such good compliments. That was so good. And if we didn't like the talk, oh god, too much for non-majority. Unprofessional. And free recombinant. I'm not sure what that means, but all right. Some people are thinking, oh shoot, I didn't know that was here on stage. I also learned how to do a cluster map. Many thanks to Nate for showing me that function. This is the relationships between these words and when they appear. And it takes a little while to absorb this. So basically what you're looking for are words that have like little squares around them and appear together. It's kind of sorting them out. So basically we have a fairly clear and well-structured goes together. There's some concepts that might underlie not understandable, inappropriate, and complicated. But if it's interesting, passionate, enlightening, exciting, we kind of group those together, as we did this time. It's pretty cool. And there was one I saw before. What was it? Oh no, the data's changed. So anyway, so that's there you go. That's what it's all. You'll see a little bit more soon. The other one was our favorite speaker one. Okay, I'm going to load this in. In total, there were 0 votes. 103 votes. Are there 103 people here? Yes. Okay, that's good. One person voted 100 times. How many people said that they learned something new tonight? None of people learned something.
That's question mark.
Oh, yeah? It just wasn't there. Okay. I'll just delete that one. Was there did you have fun questions? No. Oh man, I could have sworn I had a question. Who had fun tonight? Okay, I'll just type that in. Who learned something new tonight? Hey, 10 talks, you better learn something new. All right. What factor was the most important to decide for important talks? Was that a question? Yeah. Good. Let's see. Let's pick 15 things that people said were important to them when they just how they decided that top 3. How well the topic was visualized and phrased in different aspects. Combination between fun facts, storytelling style, passion, thoughts, and presentation. These are really good. These are really good. These are things that we value. And ninjas. And a dash. All right. How can we do better? 15 things we could do better. Okay? It's going to be comments on pizza, actually. That is good. Who wants to see this? Raise your hand. All right. The first time I've had to do this, let's take a look at the columns we have in our data set. I think there must have been a misspelling. Here we go. And now I got pictures of me live coding from 100 people. So much money. We're just going to take a random sample. We don't need to see all of them. Hey, there we go. All right. We can change the speed. Everything was cool, and he wouldn't change anything. Can't think of anything. Don't speak too fast. Right. Less dry, speaking more clearly, clear speaking, and confidence. Actually, that's good. That's good. That's really good feedback. So the talks were well structured. They were entertaining. They were passionate. All that was left was that we could speak a little bit more clearly. That's really nice. Thank you very much. All right. By the groupings that I saw before the last talk, I found 5 different awards, named awards that have. Google. Don't do this. All right, let's try that. That will be gotten, not to work with the mouse cursor. Okay? In addition, there will be a top 3 awards based on your favorite speakers. I'm going to run this code really quick before we have the speakers come up and receive their awards, because it might break and I didn't test it. And apparently there's some silence. Excellent. Okay. I'd like all the speakers to come up. We're going to clap for them. Everyone, all the speakers worked really hard for their talks. Thank you so much for supporting them and coming. Please ask them lots of questions about the research and motivate them to do more good science. Let's start with the most inspiring talk. Maria. Jose. Wow, okay. The most convincing, Antonio. The most entertaining. What happened? You don't have to walk off to the side there. Oh, we got another one. Most entertaining, Ira. Now for the big one. If you picked 3 people that you said were the top ones, regardless of the words you picked, and I have no idea how to decide who was the best. Because we keep talking about what the most fair thing is, and I just can't do it. I can't do it. I can't do it. There are 3 ways that you could have said that the top ones were the top. And depending on how you rank them and aggregate them, you get completely different results. So I'm going to let you guys decide which of the 3 models are going to be picked so we can figure out who the top 3 ones, because I can't do it. I can't do it. Either, here's the 3 models. We'll describe them to you, and then we're going to vote by show of hands. And that model is going to choose the top 3. Okay? The first way that you could have picked, you could have decided is said that, hey, we have 10 speakers, and I don't know who's first or second or third. How do you do that? How do you do first versus second? That's too abstract. We could just pick the top speaker by saying the person that was mentioned in the top 3 the most times. If the most people said they were in the top 3, then they must have been great because they weren't in the bottom 7, right? You could have said no. First was good. Second was less. We could give 3 points to whoever whenever they were ranked as first, 2 points to whenever they get second, and 3 points to whenever they're third. Then we just add up all the points. That's the second way we could do it. And the final way we could do it is by using a Bayesian method. We could say we don't know anything about the people you didn't rank. There's no information. But we do know that when you said they were second or third, then it meant they were definitely not first. So we could say that the top ones were the ones that were said to be first the most times, and just sort them like that. So model 1, most often mentioned. Model 2, ranked, and model 3, top most often. So raise your hand if you think we should use model 1. Raise your hand if you think we should use model 2. Model 3. All right. That sounds good. I mean, you took all the effort to choose which ranking it should be. We just do it.
Does it make a difference?
Yeah.
It does. Yeah. All right, you ready? We're gonna just be all 3 at once. Our top presentation is from Jose, and our 2 runner-ups are Constantine and Rachel. Give them That's all we have today. Thank you very much. Come to the after party, and please join more science labs. Thank you.
Thank you. We have certificates and we have prizes, of course.
Oh yeah, lots of prizes and stuff.
But you choose them yourself, so that's the most fair.
Can we lift up the lights, please?
With your extra.
We want to get posted.
Yeah, of course. Thank you. Okay, so wait a second. Of course, you need to take a picture before anybody from my family. We do have to try but you just choose whatever you want, and when we all are winners, and there is no winner. But it would be great if we could take pictures.
Is it working? I think basically in the end, before you all leave going after Friday party night, or maybe just take some sleep, we would like to really thank the organizers because they put in a lot of effort. They were super kind. They really pushed us through on a Monday at Google. We were like full of all the snacks and just being present at Google just flashed. And this still made us to prepare a talk in 4 hours, which was like really amazing. And they were super kind. So really a big applause for the organizers, please.
It was a lot of fun. Okay. Yeah, so you know where to find the after party. You also find us there after we clean up. So it's Stranda Bar. I put it up again so you find your way, and I hope to see many of you there. Okay? Thank you. Don't we take a picture now? I don't want to pass each other. I Can we take a picture with all of us, please? Yes. Can we make a happy picture? Yes.
For the video,
Shut up! Okay. Actually, I know more than you. Cool. So you would do that? Okay. Yeah, I think you already made some templates, so I will just check them. Someone needs to double check them.
Genau.